to light a lamp. That's like Indian tradition. And I invite all the guests, speakers to come on the stage and help us in lighting the lamp. All the speakers, please. Thank you. Matchbox candle.
या ब्रह्माच्युतशङ्कर प्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा। शुक्लां ब्रह्मविचारसारपरमाम् आद्यां जगद्व्यापिनीं वीणापुस्तकधारिणीमभयदाम्
I'll do full screen. Good morning, everybody, and a very warm welcome to all of you. So I am Arpan Chattopadhyay from IIT Delhi. I am a general co-chair of this workshop, Crossroads of Machine Learning and Signal Processing. Yeah, that's better. So before we begin, I would just like to share a brief story about how we came together to organize this workshop. So it was last year's ICASSP, in last April 2024. I was in ICASSP, and in fact actually I was a member of IEEE TWG Technical Working Group on Synthetic Apertures. So I met Professor Hari in KVS Hari from IISc Bangalore in the ICASSP 2024 conference, and he came up with this ideas that we can organize a satellite workshop for ICASSP 2025. So his idea was that we could invite reputed researchers from all over the world, so that the local researchers also get to know about their research from happening all across the world. So the idea was that probably this will help in developing new research collaborations between Indian researchers and researchers from across the world. So with that idea, we proceeded, we chose Delhi as a venue because it has a vibrant research ecosystem and it has good connectivity, so it would be easier for the speakers to attend. And actually, when we decided to move ahead with this, we approached SPS Delhi chapter. Professor Monica Agarwal is the chair of the chapter, so we joined hands to organize this workshop. So this workshop is being funded by several organizations under US DoD, specifically AOARD, WEnergy, and ARL. And I would specifically like to thank these organizations for funding, specifically Dr. James Ju from AOARD and Dr. Joel Goodman, who is also a speaker in this workshop, so from WEnergy, so they helped a lot. And then I'm also grateful to IEEE SPS Delhi chapter for sponsoring this workshop, and Professor Monica helped a lot in this. SPS Technical Working Group on Synthetic Apertures is a technical sponsor for this particular event, and many of the organizers are part of this technical working group. So here is the organizing committee details. So me and Dr. Kumar Vijay Mishra from ARL, we are the general co-chairs. So Vijay is unable to attend because of the travel advisory from US DoD. So in the steering committee, we have Professor K.V. Sari from IISc, Dr. Anantram Swami from ARL, Dr. Raghu Raj from Naval Research Laboratory, and Dr. Murlidhar Rangaswamy from AFRL. We have Professor Shobha Sundaram from IIIT Delhi as Finance Chair, Professor Monica Agarwal from IIT Delhi as Local Arrangement Chair and SPS Liaison Officer, and Dr. Chandrasekhar Rai from IIT Delhi as Registration Chair. So the story would have been incomplete without the mention of the volunteers who worked tirelessly to organize this event. So we have Mr. Satish, Mr. Yatindra, Mr. Amit, Mr. Mohit, Suresh, Ishant, Nikita, Rashmi, Akanksha, Jyotismita, Komal, Siddhant, Sanjay, Vipul, and Jyotirindra. So they worked very hard to organize this event, and a big thanks to all of them. So here is a brief overview of the workshop. So we have tried to include as many technical topics around SP and ML as possible, which are basically cutting edge. And you can see, if you look at the program schedule, you will see that we have talks on multi-view signal processing, graph signal processing, LLM, RL, Gen AI, transceiver design, federated learning, misspecified performance bounds. In the tutorial tomorrow, we will have a tutorial on cognitive radar tomorrow afternoon. And tomorrow afternoon, we will also have a very interesting panel discussion, which will talk about the interplay between machine learning and signal processing that is happening in the current literature, as well as probably it will show some directions for future research avenues. So this event will be followed by a social event on Saturday, 5th April, where all the speakers and panelists will be taken for a trip to Taj Mahal. We will start early in the morning from Delhi and come back in the evening. So I am happy to share that actually in the registration we got a huge response from the attendees. So till yesterday afternoon, the total number of in-person registrants was 108, and virtual registration was 144. This is still yesterday afternoon. Then among them, around 50 people are faculties, around 194 are students, and approximately 12 are from industry, and approximately 28 registrations are from outside India. Before I conclude, I will briefly discuss about our electrical engineering department at IIT Delhi. We have around 62 faculty members and 400 plus PhD students. It has QS ranking 47 in 2025, this department in the domain of electrical engineering. And the NIRF ranking, that stands for National Institutional Ranking Framework. So under that framework, the ranking is 2 in engineering in this year. And in overall engineering and technology in 2025, the institute's overall QoS ranking was 26. And in the department, we have a number of reputed researchers. Many of them are fellows of India National Science Academy, India National Academy of Engineering, National Academy of Science, then the World Academy of Science, etc., etc. And the department is very vibrant and it's always open to collaborate. So in case any of you are interested in collaborating with anyone in our department, or if your institute is interested in collaborating, so please feel free to contact us. So the department is always looking forward to explore these collaborations. So with this, I would like to conclude, and I would like to thank you again for attending this workshop and agreeing to speak in the workshop. And I hope you enjoy it. Thank you very much. So now I would like to invite Professor Nicholas Sidropoulos from University of Virginia to start his talk.
One second. Nikos.
Bluetooth connection?
Yes.
Let's check the Bluetooth connection.
It's working, it's working.
Yeah, it's working, I think. Yeah. Thank you very much. Well, let me take the time to thank the organizers for organizing this workshop. Thank you for inviting me. It's a pleasure to be in India, my very first time, and to be among friends, many friends that I've known for many years. All right. I think I have a big enough voice, but yeah. All right, can you hear me? So I would like to talk today about multi-view signal processing using linear and deep or nonlinear canonical correlation analysis. And whereas I usually start my talks using theory and methods, let's say, and then eventually get to applications, what I will do today is flip it around. And I will start from a motivating application and later talk about more general theory. So the application that I will start with is communication, a communication application, and particularly communication in congested and contested environments, which has become a lot more important nowadays, and you see a lot of research interest in this area. So the fundamental problem is, how can we communicate reliably in the presence of unpredictable and potentially bad interference, right? Not interference that we control, not interference that is, let's say, 20 dB below your signal of interest, but interference that is potentially 30 dB above or 10 dB above or even more. There are many applications for this, including things like Wi-Fi in congested areas, reducing the frequency of a commercial FM or TV station, dealing with interference from a powerful source, such as radar, which is particularly important nowadays because of the interest in joint communication and sensing. Or, for example, think about the Federal Emergency Agency taking over to broadcast an emergency message without having time to clear the channel from a legitimate user, right? So how can you accomplish communication in this regime? So if you have a signal processing background, you know, there are a lot of things that come to mind. One is potentially using array processing tools, beamforming tools, signal separation. Unfortunately, these do not work well. Actually, they do not work at all when you have low and varying signal to interference plus noise ratio, particularly when you have intermittent on-off interference. Right? You can think about error control coding, but this is designed to handle random errors and not systematic interference. Right? You can do spread spectrum if you want, but if you are operating 30 dB below, let's say, an interferer, you need 10 to the 4 spreading gain at least, which sends your data rate to 0, or in fact you have to open up your bandwidth and take in a lot more interference, so that will not work. Another idea that might come to mind is known as interference alignment, which is an interesting, elegant idea theoretically, but not practical for a number of reasons. So, because it requires control of the interference and tight coordination between the two systems. So there's been a lot of work in this area, right, on dynamic spectrum access and cognitive radio, but nothing practical that really came out, right? And a couple of years ago, as I was driving back home from work, an idea occurred to me, which was a starting point behind a lot of the work that I will be talking about today. So let me give you sort of the bird's eye view of this idea. So in modern digital communications, we communicate using vectors, basically, sequences, right? Baseband equivalent signal sequences. So you have a sequence of +1s and -1s, or some other finite constellation. You do pulse shaping, right? And you communicate effectively using vectors, right? When there is interference, you may have, let's say, this orange little vector, which is a secondary signal that you are trying to decode, right? Observed in the presence of strong primary interference. This is the blue vector, which is much longer, let's say, than the orange vector. What you observe is the black vector, and you are interested in recovering the orange signal, which is tiny relative to the primary interference, right? So, in fact, this black vector is a linear combination, right, of the two signals of interest, which depends on the channel gains, right, between the primary transmitter and the secondary receiver, right, the secondary receiver being interested in recovering this signal, and the secondary transmitter and the secondary receiver. So this is what you observe, and it is very, very difficult to get this. Now, if you have a second antenna at the receiver, you will get two linear combinations of these two signals, right? So you will get 2 points or 2 vectors in the subspace spanned by these two signals, but you don't know what the orange signal is. You can find the subspace, but not the signal of interest, right? So here is the key idea. Suppose that you transmit this signal twice. In the first transmission, you are hit by this interference vector, and by using 2 receive antennas, you can actually estimate a basis for the subspace of these 2 vectors. If you repeat the transmission, you transmit the orange signal again, right? But the second time the interference has changed, what you will get is another subspace basis. Battery went out. Here you go. So in the first transmission, you will get a basis for this subspace. In the second transmission, you will get a basis for this subspace. And guess what? If you could intersect those 2 subspaces, right, the signal of interest, right, is aligned, is proportional to the intersection, right, under very mild conditions, no matter how powerful the interference is and how small the signal of interest is, right? So if you could intersect subspaces, right, if you could transmit twice and intersect subspaces, you could recover no matter what, under certain conditions. And this is the basic idea. It's pure geometry. I thought of it initially algebraically, but geometry explains it, I think, very clearly, right? So mathematically, let's write it down now for some algebra and see what is the connection to multi-view signal processing and canonical correlations. So what you have mathematically, if you use 2 receive antennas, right, you transmit your orange signal once, and it is hit by this primary interference. You receive it through a 2x2 matrix, channel matrix. You transmit it again with a different interference, the green interference this time around, and you get a different matrix mixing the 2 signals together, and you now have two matrices, this blue matrix and the green matrix. If you transpose them, right, they can be written in this way. So you see that the first view of your signals comprises the signal of interest with some blue primary interference, right? And these two are mixed with some channels, right? The second view, which comes from the second transmission, right, comprises again the signal of interest mixed with a different interference, right? And then you take linear combinations with two different channels, right? And the point is that if you could intersect the span of these two matrices, you could get the signal of interest, right? And I will show you under what conditions this will happen, right? And the way you intersect subspaces, by the way, all of you, I'm sure you are very familiar with linear algebra, right? But I don't think you were told, I didn't know at least, how you intersect subspaces, right? And how you intersect subspaces is through this optimization problem, right? So basically you take the two views, y1 and y2, you take a linear combination of the columns of its matrix, and you want to generate the same one-dimensional signal, the same column vector, right, out of both matrices, right? So you are trying to find something that is in the span of both matrices, right? And you need to somehow control the norm, right? Because otherwise the trivial solution is g equals 0, right? So you want to avoid the trivial solution, and you have this formulation. All right. Now, so this is subspace intersection. This is how you do it algebraically. You may wonder, what does this have to do with canonical correlation analysis? So let me remind you what is canonical correlation analysis in the simplest possible form. And that is, I give you two vectors, vector x1 and vector x2, comprising multiple random variables, right? And you are trying to find the two linear combinations, right, of those variables, right, and the other variables, right? Two linear combinations of the two random vectors that will generate the same random variable, or two random variables that are as correlated as possible, right? So this is the simplest version of canonical correlation. So what you are trying to do is find a latent random variable that sort of underpins both random vectors. So that's an old problem. In reality, you are never given, joint statistics, but you are given realizations of these two random vectors, right? So in practice, you are given two matrices containing n matched or jointly drawn realizations of vectors x1 and x2. You stack them in two matrices, and then the least squares version of canonical correlation analysis that solves this problem up here. You're trying to find, right, two-dimensionality reducing vectors q1 and q2, right, that will generate essentially the same vector from both views. It is not difficult to solve that this problem is equivalent to this problem by introducing a slack variable g, and by using this constraint, you can transform it into this version, which shows clearly that what you're trying to do is maximize correlation between the two derived random variables, right? So this is the simplest version of canonical correlation analysis, and it amounts to subspace intersection. So what canonical correlation analysis does is intersects subspaces in a least square sense, right? So this has been around for over 100 years. I haven't seen any mention of this fact in the literature. You can solve this problem using singular value decomposition, so it's computationally efficient. But the question that has remained open for many years is, okay, so suppose I have a latent random variable that is common, or maybe a few more. Let's say I have 3 latent random variables that are common between the two random vectors, right? Under what conditions will this formulation tease out uniquely those random variables? The identifiability question, right? So that has remained open for many years until our work came in a few years ago, and we have pinned down conditions under which this happens. I don't have time to go over this in detail, but the conditions are algebraic and they are relatively easy to satisfy. So basically what you need is full column ranks of the mixing matrices, and if you have that in full column rank of the signals, then basically this is unique. All right, how do you solve the problem? In the more general case where you are trying to extract more than one common random variables or more than one-dimensional common subspaces, the formulation is this, and it is known as the max bar formulation. Here we have more than two views. We have a total of capital I views. And what you are trying to do is find matrices, dimensionality reducing matrices Qi, right? Which when they hit the views Xi from the right, generate the same matrix G, right? And G is constrained without also generality to be a basis.
But how do you get the S? The primary interest is to find S, right?
In the previous application, right, the primary interest is to find S. So what you get from the intersection is S, right? So basically when I solve this problem and get G, right, G is proportional to S. It's the same vector as S up to global scaling. So by solving CCA, you get G in that case. If it is one-dimensional. If it is three-dimensional, you only get the span. You cannot get anything more, right? So there is rotation ambiguity. So if you have additional properties, you can actually take care of that. If you have finite alpha constraints, for example. But what I will be talking about here in the communications application, you can always make sure that it is one-dimensional. So you actually recover the signal, right? Itself up to global scaling, right? And you need a few pilot symbols for that. Okay. So let me skip that in the interest of brevity. Now, many of you know me for a theory and methods person, and I am, right? But a few years ago, I decided to actually try it out in practice. And so together with my students, we bought software radios, and we set out to implement this in the lab because it is not particularly difficult, right? So the kind of processing that we need to do is SVD-like, a principal singular vector computation, right? So in fact, what you see here is the test bed in our lab. You have a primary transmitter, a primary receiver, a secondary transmitter, a secondary receiver. The secondary receiver has to use at least two antennas, and they have to be synchronized. And we implemented this in practice. And these are the results. What you see here is the symbol error rate of the secondary link as a function of the signal to interference ratio. So what you see here is the transmit power difference in the lab, right? In decibels. So when it says minus 40, it means that the interferer is 40 dB stronger than the signal of interest, than the secondary signal, minus 30 dB stronger, etc. Right? So this is powerful interference. We go all the way up to minus 20. And what you see is that for interference powers up to 35 dB stronger than the signal of interest, right, you essentially get the optimal performance, right, which is remarkable. Right? We have pushed this down to minus 45, so 45 decibel difference between primary and secondary transmitter. So this is interesting because there is no other known way to communicate in this regime. You are using a channel that is hit by a really powerful interferer, which can actually fluctuate in time, right? It can be 20 dB lower than you, 50 dB stronger than you. You don't care. You continue communicating, right? Through this strategy. In fact, you can use the repetition structure to solve the synchronization problem, which is, if you are a communications guy, you know the weakest link is synchronization. Right? Once you acquire synchronization, the rest is relatively simple. It is actually immune to CFO due to shift property of contact exponential. Right? You don't need to estimate any channel whatsoever. You don't need to coordinate with the primary. Primary could be a radar hitting you. Right? You can actually do a lot more things with it, but I will. The practical limit here is the resolution of the analog to digital converter. It was 12 bits per in-phase quadrature in our experiments. You don't want essentially the dynamic range to be so high, right, due to the interferer, that you throw your secondary signal below the 8D quantization limit, right? So if you avoid that, you can deal with very powerful and time-varying interference. Very, very briefly, because I don't have the time to go through it. So what is the moral of the story? The moral is, let me transmit my packet twice, and I can get away with murder. I can deal with any interference, right, that comes to me. I use a second antenna. The flip side, of course, if you are a networks person, is you know that, first of all, if there is no interference, transmitting the packet twice is wasteful. If there is interference, transmitting it once, retransmitting it once may not be enough. So ideally, you want an adaptive mechanism that will help you decide how many times you need to retransmit. And in fact, then the problem becomes one of generalized multi-view signal processing, known as generalized canonical correlation analysis. And so how do you do it? It's actually quite simple if you think about it. You can use the ARQ mechanism, which is actually present in every system we have, Wi-Fi, 5G, you name it. You can use the ARQ mechanism. The ARQ triggers retransmission every time communication fails, right? And when you trigger a transmission, you collect the data from all the transmissions. Instead of decoding it the way they do right now, the networking folks do, use canonical correlation analysis for the decoding. And if you do, your throughput can go up 100 times, and your delay can go down 30 times relative to not using CCA. And it's actually completely backwards compatible with the ARQ protocol. Because all you do is change how you decode the receiver, basically. All right. I would have played the demo of actually we implemented a secondary FM transmission under our local most powerful FM station. And it was successful, but I didn't get permission from my student to upload his video because I didn't have the time. So I'm not going to play it out, but I can play it out to you later if you are interested. It's a very interesting demonstration under an actual FM station, right, in our lab. So that was the motivation. Let's talk about other applications of multi-view signal processing and canonical correlation analysis. So one that we worked in several years ago is to finding the task-related response, right, in fMRI data of people presented with a particular stimulus. So if I show you a picture of an apple, right, your brain has a certain response. Okay. So if I take the fMRI of your brain, let's say, while I show you the picture of the apple, right, your brain will have a certain response which is overlaid in background responses. It turns out that all of us here have approximately 40 to 50 dimensional common subspace in terms of background brain activities, right? Which happen all the time, but they happen with different temporal variation, right? So we listen to music, we are thinking, we think about our families, whatever, right? So all this creates background processes in your brain, right? But the amount of each process, the activity of each process varies a lot from individual to individual. However, at the moment that I show you a picture of my friend Yorgo, right, you all have the same elicited response, right? Because you recognize his face, right? And then you have the same spatial response in your brain voxels and the same temporal response, approximately. So we are interested in teasing out of this brain activity what is the part of the activity, right, spatial and temporal, that is elicited by the stimulus. Right? And this is the same problem, fundamentally, with a twist. The same problem as I described in the communication application, but with a twist. So what we do is we vectorize the fMRI. So we have all the voxels here as rows, and time are the columns. In fMRI, we have a lot more voxels than time measurements, typically, right? So this is a tall matrix, and that is important for reasons that I will mention shortly, right? So we model this data as a sum of outer products, right? So every spatial response is a column vector because we vectorize the voxels, and every temporal response is a row vector. So we model the data as a sum of spatio-temporal responses. And if you want to write mathematically the model, This is the fMRI of, let's say, myself, right? So this is voxels by time. And we model it as a rank 1 factor that corresponds to the stimulus, right? It is common in space and in time for all the subjects taking the test, right? And then you have other contributions, right? The other contributions are the 40 or 50 different spatial processes that are going on in our brains, which are common, but every one of us has different temporal activation patterns for those common spatial responses. And then you have unmodeled dynamics. So the overall model is this, right? We are interested in this rank 1 component that is common between all the subjects, right? So if you manipulate this a little bit, you will see that what you get is effectively this, right? So you can collect the spatial profiles, the little a and the capital A together, right? The temporal profiles together, right? And so if you take a look here, right, you will realize that these matrices have a common, right, temporal component that is common to all the matrices. And the moment you see this, now that I gave you the previous application of CCA, you say, hey, life is good. So I simply run what I did before for communications, and it will give me the temporal component, right? S. And once you find the temporal component, then you can do a lot of things to find the spatial component. But the answer is no. And it is no because this matrix is tall. So essentially, in terms of temporal components, you span everything, right? So what is common in terms of temporal components is the entire space. So you cannot do it like this. It requires a more sophisticated approach, and that is you do canonical correlation twice. In the first step, you actually intersect the column spaces, right? And through this, you get beam forming, let's say, matrices QK, which in fact span the corresponding temporal components, and then you do canonical correlations once more, and you get the estimate of the temporal component. So it's a two-step process, and both steps are multi-view canonical correlation. How well does this work? So neuroscientists have a model which they sort of fine-tuned over, 30 years, which tries to predict the solicited response when I show you a picture of somebody or an apple, right? And that model is shown here in blue, right? So this is the model-based approach from neuroscience. And what you see here, all the other curves, are the temporal responses, the common temporal responses estimated from all the subjects in our study. And you will see that there is a very close correlation between the two, right? So this is model-based and assumes knowledge of the stimulus, and all the canonical correlation stuff does not assume knowledge of anything. It's pure algebra, right? And it actually matches very well. This is when I said, what is the common subspace dimension of our brains? You will see here that it's approximately 40 to 50. So there are 50-dimensional common processes happening behind. And in fact, neuroscientists who have studied our method really like the results, but I'll skip that for now. I have maybe 5 or 7 minutes to go, and I would like to talk about deep canonical correlation analysis, right? Which sort of brings you up to sort of modern day, even though linear canonical correlation, trust me, is much more powerful in many, many ways, right? You can say a lot more things, and it has a lot of applications. But the nonlinear is interesting from a research point of view, and it has some interesting applications. So sometimes, now you may notice that canonical correlation assumes a linear model. To be correct, it assumes a bilinear model, right? But that model is restrictive. So there are applications where you have to assume that instead of linear transformations to deduce the dimension, you need nonlinear transformations. Right? An example is articulatory measurements of speech combined with speech signals, right? And you are interested in finding common factors. So this has to be a nonlinear multi-view analysis, right? So I will talk about primarily deterministic deep CCA methods. And the original idea behind deep CCA was the following. Instead of using vectors Q1 and Q2 that will do the dimensionality reduction and uncover or tease out the common component, what you will do is assume functions, right? Which are nonlinear functions, F1 and F2, that will take the two random vectors as input, give you two random variables that are maximally correlated. Hey, it sounds simple enough, right? And that's what people did. This goes back to Andrew in 2013. The problem is, and then following that in 2015, Wang and others, right? A more generalized version of the problem, if you are trying to extract more than one latent variables in a nonlinear fashion, is this. So you, essentially, if you take the properties of a trace, this is the expected, the sum of correlations, right? And under orthogonality constraints. The problem is that trivial solutions may occur. And it is very easy to get trivial solutions when you allow nonlinear mappings. Let the mapping map you to one, no matter what the input is. Perfect correlation, right? Perfectly useless, right? So you have to be very careful to avoid trivial solutions. And people didn't do this in the beginning, but later on realized what is happening and tried to correct that. And so the original approach to avoid trivial solutions was to introduce a regularization term, right, similar to autoencoders. So you are doing dimensionality reduction, which is nonlinear, right, and you are using a neural network to model those nonlinearities, hence deep canonical correlation analysis. And you want this dimensionality reducing operation to be approximately invertible, so that it retains the essential information, right, in the input data vectors. That is, in a way, right, a trade-off between common components and principal components, because the reconstruction term sort of forces you to pick principal components, nonlinear principal components, right? Whereas the canonical correlation term, the common component, right, might in fact not be a principal component. For example, in the brain signal, the component that you are trying to find is certainly not principal. So if you focus on principal components, you may lose common components. So that is a drawback. There's been several generalizations of this. One is deep generalized canonical correlation analysis, which actually, this is this formulation, right? So it is in a way inspired by Max Var. You are trying to find nonlinear functions, right? That all of them generate the same vector G from all the views, but still trivial solutions may occur, right? And generally speaking, there are no identifiability guarantees, which is a problem, because you don't know what the heck it is that you are teasing out, right? And identifiability is our sort of specialty. So I will very briefly mention these results, and I will stop there with one example, right? So first, my former postdoc and very good collaborator, Xiao Fu, and one of his students came up with the first identifiability proof for deep CCA. And essentially, they cast this problem in a probabilistic framework, and they say the following. Assume that each one of the views, right, is generated by a common random vector G, which affects both views, and then individual or private component random vectors C1 and C2, right, that only affect one of the views, right? And the assumption here is that these three are independent random vectors, meaning that they are block separable. The distribution is block separable. Then, under some additional technical conditions, you can prove identifiability of this model. Although identifiability here cannot be recovering G, because by allowing nonlinear transformations, you have to allow, in your identifiability proof, invertible transformations of the common component. But you can at least prove that you can recover an invertible transformation of the common component. Finally, together with one of my students, Paris Karakassis, a few years later, we consider the generalization. And our generalization is in the same, let's say, probabilistic graphical model framework. Our generalization allows for the common component and the private components, right, to have a more general distribution. It's not separable, so the private components are not independent, but they are conditionally independent given the common component G. All right? And under this model, we can again prove identifiability and come up with suitable algorithms that do it in practice. I have to, I'll skip the details. Just to give you an example of a case, of a multi-view signal processing case, where you can assume conditional independence, but you cannot assume independence, right? So this is actually a commonly used example in multi-view signal processing. It starts from the noisy missed digits, right? So you pick a digit label from 0 to 9 at random, and then you construct two views. The first view, right, you pick an image having that label at random, right? And then you rotate it by a random angle. In the second view, you pick another image with the same label, right? And then you add random noise, right? So these are the two views, right? So this is view 1, view 2, right? So you pick an image of a 1, you rotate it at random, you pick an image, another image of a 1, you add noise at random, right? And you are trying to find the common factors. So what are the common factors here? The label information, which digit you picked, is a common factor, clearly, right? The rotation and the noise are uncommon and they are independent, clearly, right? However, the shape is uncommon and conditionally independent, but not independent, right? Why is it conditionally independent, right? Clearly, you picked, let's say, ones, right? Both are ones. They are not independent, right? But the particular realization of one that you pick, right, is conditionally independent given that you picked one, right? So that's a far more general model. Okay, and we have very good results in terms of accuracy and other standard metrics, but I'm running out of time, so I will stop here, and I'll be happy to entertain any questions that you may have. Thank you.
So the CCA problem that you said, right? You said it's solvable by SVD. It has a closed-form solution.
Yes, it's solvable by SVD. In the communications case that I was talking about, in fact, you can prove that the complexity of solving it is nm squared. N is the packet length. M is the number of antennas, which is typically 2, 4, 6, 8, so it's small, right? So it's actually complexity that is not unreasonable, and that's why we can implement it in the lab, right? Not in real time, but in quasi-real time. Yes. Al.
Just a follow-up. In PCA, there's a well-known... working, I don't think. Yes, it is. PCA, there's a well-known way to accelerate, which of course is an iterative version, right? Where you basically iterative PCA, sometimes called online PCA, yes. Where you can do things recursively, and therefore maybe the initial complexity is nm squared, but then per time point afterwards, when you get repeated interference, you can reduce the PCA complexity to basically nm, right, order nm. So does the similar type of reduction occur here?
Yes, Hyderabad. You will see.
Okay.
So, and this plays a role in the synchronization problem, because in synchronization you have to try this and that and that and that, so that you have a sliding window, and then you have to find the right synchronization where you will get high canonical correlation, right? So that problem is of interest to us, right? And it can be dealt with in a number of ways, reminiscent of RLS, right?
Exactly,
In fact, several people, Ignacio, for example, Santa Maria, has done work back in 2007 on an infinite horizon discounted problem of this kind. We looked at it from a sliding window perspective because that's a communications problem. But yes, you can do all the standard tricks because at the end of the day, CCA reduces to principal component.
Yeah.
Therefore,
Right.
whatever you can do for principal
Principal, you
component,
can do
do
that, yes.
here as well. The only difference is that we have cross correlation matrices to worry about, but you know, the same more or less philosophy applies. Yeah.
Great. Thanks.
Just one curious question. There's something called FAR PCA. FAR.
FAT PCA.
FAR.
Fair PCA.
FAR PCA, yeah? So you have two.
Yeah, I
two
heard about
things,
it.
okay,
Yeah.
and then you try to find the components which are FAR to both of them. So it's solving a min-max problem or a max-min problem. This is something, you try to find a common space between the both, right? Is it similar to FAR PCA?
It's not similar to fair. You are talking about fair PCA because I have a student, Aritra Connor, who's working on that, and that's how I know about fair PCA. No, it's not related to that, to the best of my understanding.
The problem is same. Like you have two matrices, y1, y2. They share a common subspace here. You try to find a common subspace, right?
Yes.
There the problem is different. Like you have two different data. Instead of putting together and find a common principal component, you try to find some sort of a fair principal component between both of them, which is fair to both of them.
Yeah,
Because,
my understanding of fair PCA is slightly different. I thought that fair PCA is one in which essentially if you cluster nodes, right, you will get, let's say, a fair proportion of nodes from two different classes. That was my understanding of fair PCA, but I'm not an expert. So I don't know the answers to your question, but if your problem can be posed as a subspace intersection problem, then yes.
they do that.
Yeah, if it is, then yes, right? And in fact, because that's what CCA does, right? So, yeah.
So you mentioned about only two things. Like, but if it's more,
Same. Well, let me qualify it. If it is more, then there are multiple formulations of CCA. One is the two prevailing ones. One is sum core, sum correlation. The other one is max var, right? Sum core is NP hard for more than two views. Max var is always polynomial time, always reducible to the principal component kind of problem, right?
still solvable by SVD.
Still solvable by SVD, the max var formulation, right? The sum core formulation is NP hard. Why you would prefer sum core from max var is a nuanced problem, but in practice, because it's NP hard, we always use max var, right? Yeah, and actually, my identifiability results hold for the general case, for any number of views, and identifiability obviously improves with a number of views.
Okay, thank you, Professor Sidiropoulos, for the exciting talk. Thank you very much. So I would like to invite the next speaker, Professor Pramod Varsne from Syracuse University. He is going to talk about copula from signal processing to AIML. Welcome, sir.
First of all, I'd like to thank you for the invitation to come here. It's great to be back. I spent a year on this campus, 1984 and 85. The place has changed completely, so I couldn't recognize the buildings and everything. And my friend Surendra Prasad is here, so thank you for coming. So what I'll try to do here is about 15 years ago, I came across Is this a better place? Let's try this. Okay. So about 15 years ago, I came across this tool called copula theory. So I decided, and I'll give you what it is and the context under which I started looking at this tool. And I was doing a lot of signal processing type of work, but then currently a number of people are using it for AI applications and so on. So I'm going to sort of talk about, just give you one or two nuggets as to where people are using it currently. And I'm a simple person, and this is what I'm doing these days. So I enjoy reading stories to my grandchildren, and a few of you know Love, so it's his children here. So, so now what is the connection with all this? Well, I read stories, so this is one of them. And so the story is that of 6 blind men and an elephant, and all of us have heard that. And so what happens is that these blind men go to this huge thing, and they look at, they sense the tail here, they sense the other aspects. So the goal here is collectively they need to figure out the situational awareness. What is this object? What is going on? So that's what we do, at least in my case I do, that we have a lot of sensors, and these sensors have a limited field of view, and collectively we need to figure out what's going on. So that's the context, and that's where I start, and that's where my copulas and so on were applicable to me. That we have a certain phenomenon. We are trying to use heterogeneous sensors, different modalities and so on, and then they process the information, send it to a fusion center that comes up with a certain kind of inference, I mean detections or tracks or estimates or what have you. So a number of us, like we started looking at it in the early 1980s, and we tried to work on it. But most of us, what we assumed was, and that came up here about correlations and so on, what we assumed was that the observations were independent. However, these observations are dependent. So this tool, copula, that allows us to somehow exploit or model the dependence, and that's what, I mean, like basically what I'm going to be talking about. So I'll define what that is and so on and so forth. So that's the context where I started, but there are many, many other applications where people are applying them, as I said, AI and so on. So the outline is that I'll give you a brief introduction, how we define statistical dependence and copula theory copulas, and then inference has been my application, that's more signal processing. But then some of the more recent work about using neural networks to realize copulas comes here. Some applications that I have recently in remote sensing, change detection, and so on, I'll talk about and then conclude. What I'll do is I'm not going to be doing, because of lack of time, a lot of details. So if you are interested in any of them, talk to me afterwards and I can point to the appropriate work. So you might feel that I'm not covering things, so just headlines you will see, and then I'll keep moving. So, so basically, when we talk about dependence, so first of all, many of us, I mean, to make things tractable, we assume independence, and in that case, if we have n random variables, then we assume independence and we can write the joint density function as the product. So that's what we did, and we do that for tractability. But then, like, I mean, in this case, we can use, like, if we have heterogeneous sensors, we can use disparate marginals, but not statistical dependence. So then the next step is, of course, we can do multivariate Gaussian. And in that case, I mean, the marginals are Gaussians. Models depend on the Pearson's rho, the correlation coefficient. However, this only measures linear relationships. So that is what I'm going to come to. So in this illustration, we have a couple of scatter plots, and there are 2 random variables. For this data, rho is 0, but visually, you certainly know, you can see that x and y are not independent. There is some structure, some dependence. So that's basically what I'm saying, that correlation coefficient is not able to capture the dependence if it is higher order dependence. So then what are some of the measures of dependence? Something that Nikos mentioned about concordance and so on. So there are rank-based measures, and Kendall's tau and Spearman's rho, they are a couple of measures that do that. And the definition is here. As I said, I'm going to be not spending time. It's just if you are interested, please talk to me later, or we can do that. Relative entropy is another measure for defining dependence. So what it does is it tries to define the distance from the product distribution. So multi-information, for example, is the multivariate extension of mutual information. So once again, you're trying to find out the distance in a way between the product distribution and your distribution. And then there is this normalized measure, so that this is between 0 and 1. Relative entropy, it's Joe's paper, and so on and so forth. So again, there are references and so on. So here is where popular thing starts. So Sklar, in the 1950s, he came up with this theorem, and essentially this allows us to capture the dependence. And let me go to the next slide, because this is much easier to explain. So what this does is, so that was the CDF, cumulative distribution function. If we take the derivative, then if there are n random variables, so, and if I want to write the joint PDF, then one can write it as the product of the marginals, which we would have done if we had independence. However, based on Sklar's theorem, we have another term which we call popular density, which is a proper PDF, so area under that is 1 and all that sort of thing. And this captures the dependence part. If that C is 1, then we are down to independence. But in most data, so it is a data-driven thing. So we can learn the model from the data. So this, like, as I said, I started looking into it 2009, 2010. And this was something that was derived or learned from the data. And I'll talk about a little bit more. But so this is what allows us to capture more information, if you will, from the data. And we go from there. So as far as the history is concerned, several copulars have been proposed. And there is a book by Nelson. There is, in fact, a 2013 edition also. And he defines, there are a number of copulars that are defined in the book. Now, this is something that I have to say, that copulars were used in econometrics quite a bit, finance and so on. And this David Lee pioneered the use of the Gaussian copula. However, in 2008 or so, there was a meltdown on Wall Street, and copula theory was blamed for that. That basically the predictions or whatever that were made, it was the fault of copula theory, not humans who used the wrong models. So anyway, I had to say this. So again, for students, for sure, do not apply theory without understanding the implications and assumptions and so on. I mean, blindly don't do that. Otherwise, this would happen. And this was a major situation. So I'm going to talk about a pictorial example which essentially shows that we can model skewed dependencies. So here, if we had a bivariate normal, it's a nice looking, symmetric, nicely this thing, not unskewed. However, if we have a bivariate density normal marginals and Gumbel copula, then you can see this is the contour plot. And you can see that we can model skewed dependencies. Another picture. In this case, we have, so in this case, we have the two marginals are normal and gamma and Gumbel copula, and it does this sort of a dependency. So this we couldn't do with multivariate Gaussian. So if the data is such that we have such sort of dependencies, then we were really not using either not using the right model, or we could have done better with use of better models. So that's what this is. So just to summarize this, copulas are typically defined as cumulative distribution functions. There is a class elliptical copulas like Gaussian and student T and so on. And then there are, and this comes from that book by Nelson. So you can, that's where you will find them. And then there are forms, and from the data one can learn all this, learn the model. Okay. How is it done? There are many ways of doing that. So the learning, there are these APICA information criterion and so on. So a number of these criteria. So these are based on minimum description length principles. One can do this, that you have a joint likelihood and then you have a penalty term. So you want to control the model complexity. Then here is another approach. And finally, area under the curve. So you can train the model. You take a lot of data and then try to find out of the list of copulas. So towards the end, I'll talk about that was not flexible enough. So I'm going to move away from just having a dictionary or library of copulas. So here, you basically try to maximize the area under the curve, pick that copula out of the list, and then the associated parameters, so that you are basically maximizing this area under the curve. So that was the kind of thing. So now let me talk about some examples. So as I said, again, there is much more to it, and if you are interested in it, let's talk offline. So some applications. So this work was done with Army Research Lab, Raju Damarla. So you will know that work. So, and I'll talk about it in a minute. So one can do biometric authentication based on different modalities. This I'll talk about because this was kind of an unexpected outcome of what we were doing. And here, nuclear, like if somebody like a dirty bomb is being carried in a truck or something and you have multiple radiation detectors, then like fusing them, one can show that one can do better. So just a little flavor of what I'm talking about. So let's say that we are dealing with a binary hypothesis testing problem, and we have two hypotheses. And traditionally, we would have just stopped here or here, but now there are these additional terms. So, and in this example, all the distribution parameters and copula information, meaning which copula, as well as the parameters associated with the best parameters. And we using MLE, etc. So the kind of form that comes is something like this. So, and I'm just showing it to you that how the usual likelihood ratio test. So this is what we would have had. So that would be the generalized likelihood ratio under independence. But then this term is something that we did not use earlier. I did not use. And therefore, the structure of the test becomes something like this. We compare it to a threshold. So the copula-based test statistic, which is this, that this is the likelihood ratio, it decouples the marginal part, which was this, which is under the independence assumption. And then, again, in this paper, we talked about some information theoretic analysis and so on, and there are some results. But the idea is that what we had likelihood ratio, it is still a likelihood ratio, but we have an additional term that is capturing, or that is based on the dependence information that we can use. So this was the Raju Damarla at Army Research Lab, and essentially the problem was this, that if like we were trying to, let's say an indoor facility, we want to know if there is some activity, if there is somebody in there. So we lock the building at night, and then instead of cameras, we leave acoustic and seismic sensors, and based on that, we try to determine if there is an intruder there. And outdoor, it would be that you have like this building is to be protected, and then you leave some acoustic and seismic sensors. Based on that data, you try to determine intruders. And actually, in this work, we were able to also classify, is it one person, multiple persons, a stray animal, or a person with a pony, or what, many classes we were able to do that based on like these two sensors. And just this, the ROC here, you can see that individually, seismic sensor would have been here, acoustic would have been here. If we had just product fusion, we would be here, but using copula, we improved the performance. So this is what we were leaving on the table. And exploiting copula, exploiting the dependence information, we can do better. So that's the moral of the story, and I think I'm going to show you. So this would be the decision fusion route, for example, that individual sensors are giving you yes and no, like tentative decisions, and you want to combine them. So that would be at the fusion center. So originally, this is what you would have had under conditional independence assumption, but there is another term which is because of correlation or statistical dependence, and using that, once again, you can improve performance. So here is a quick example of that nuclear thing. So the distributions here are not all Gaussians and stuff. So let's say that over here we could have like the Poisson model in Gaussian noise. So that would be one model of the source, and the other could be hierarchical Poisson gamma. So this lambda sub ij could be a gamma distribution. So again, these are the types of models that are used in physics, radiation sources and so on. So the thing is, and in this case, these are infinite Gaussian mixtures. So again, I just wanted to say that not all problems are signals in Gaussian noise. There are more complex models and so on and so forth. So once, just an illustration that for that problem of nuclear thing detection, and then the model is just the Poisson model, then with under independence we were here, but if we use the dependence information, we can get up there. So that's the kind of thing that I wanted to show. All right, this was quite satisfying, and this was totally unexpected. So, so first of all, so the way it came about was that co-author, I guess it's on the next page, Justin Dowells, currently he's at Delft. So he came to Syracuse to give a talk, and he was talking about this problem. And the problem was early detection of Alzheimer's disease or mild cognitive impairment. And my student Satish Iyengar suddenly thought of things, and then we talked to him, and then this is the result of that work. So in like trying to look for neurophysiological disorders, one approach is to use an EEG. So you basically put these electrodes on the head, and then what you are getting out of are these series, time series data. So these are the time series coming out of each individual electrode. And what one looks for is neural synchrony. So if there is an activity here, is there activity in neighboring time series or not? And this describes basically, so there is a baseline, if that neural synchrony, which I think it is used like Granger causality is like one type of measure that that does this. So if it's a baseline, that is typical human, let us say. Now, if the neural synchrony is higher than the baseline, that's an indicator of epilepsy. If it is lower than the baseline, then it is indicator of Alzheimer's disease or heading there, or mild cognitive impairment and so on. So that was the thing, and then the Justin Dowells and so on, the things that they were doing were, again, they were not utilizing dependence, the spatial dependence across the time series. So then my student Satish and so on, they worked out the thing, and essentially what we did is we defined, like multi-information was used as the measure, and it was estimated basically empirically, in this case And then the joint density is needed here, and that is based on the copula and product and so on and so forth. So that was the implication, that was the application of using copula on top of existing neural synchrony measures. And we were able to, I think it's the next slide, yeah. So we had actual data from Riken Institute in Japan. There were 25 patients with MCI symptoms, let us say. 38 was the control group. And we were able to improve the accuracy of classification from 80 to 85. So again, utilizing dependence information, one could do things. And we were leaving these sorts of things on the table. We were not doing that. Okay, so that was that. So now more recent stuff is something where we are trying to see how we can do. So up to this point, we go to the library of copulas, the dictionary of things, pick one, estimate the parameters, and go on. But that may not be enough. So here is a couple of scatter plots. And in this case, we have like symmetric dependence, and there we have tail dependence. So the copulas in the dictionary that we had, some of them, the elliptic ones, they model this. And the other ones, the Archimedean, they model this. But we were forced to select only one, either this or that. So there has been work over the last 2, 3, 4, 5 years that people are trying to say that how about if we mix them? So mixture copula, and that is the that was the thing that people did. So as I said, I mean, so this group, it essentially models symmetric dependence. This group, which was the Archimedean, it models the tail dependence. So then why not mix them together with a weight? And so this would be a mixture copula. So you do that. And as I said, there have been people who are looking into it like 2022, 23, and now. So this is one direction that people have gone. So the application that so this thing is on remote sensing data, and we are trying to look for change detection. So, by the way, so yeah, these are some the contour plots. So this is more like a symmetric thing. Here it is tail dependence. By mixing them, the contour shows that we can capture both symmetric and tail dependence. So that's the idea, that mix them and you get more flexibility. But next thing would be that use a neural network to learn it, which is even better. So using this, there is some data. So this is a flood data. And this is like an existing algorithm. And with using copula mixture, so yellow is better. So that means it gives you a higher confidence saying that there is a change. So this is change detection. So over the existing good or benchmark, one can do much better. I don't have anything that if we had just one copula, then what would have been there. So the mixture, how much improvement we get just by using mixture, that picture I don't have. Okay. So now comes that story that I was saying, that we had this copula library, even though I just talked about the mixture, but this was a fixed one. So this was finite, manually populated, and we selected one of them. Okay. So the limitations are, so again, with this traditional copula, meaning that dictionary, fixed mathematical form, you select one, fine. So then why not utilize, like generate the copula? So this is a nonlinear function that you are trying to learn. So do that. So you generate that. So it gives you the flexibility and you generate rather than select, and it's better interpretability, why, what, and so on. So those kinds of things happen. So using, and the approach would be that the neural network itself will be the copula cumulative distribution function. You use the gradient, which is the PDF. That's your back propagation gradient. Then since it has to be a PDF, it has to satisfy things like like CDF boundaries 0, 1 to 0, 1. It has to be non-negative integration has to, so the constraints and all that. So you basically do all this standard way of learning. So you learn the copula function through a neural network. So it is, how should I say, it is more flexible and more accurate. Yes?
How do you impose these constraints on the output?
During the optimization. So it is like the iterative thing, you put constraints and you keep, like, it's back propagation, you keep going. These are some pictures of a scatter plot. If it was from the library, it might show you something like this. This is another one that with just Gaussian copula, you will have this, but with neural, you can make it much more accurate. So that is what is shown here. And so the change detection thing, just the concept, I think I am okay with time, right? Yeah, I'm okay. So I'm almost done. So that's good. So now, if there is a change, so let's say that these are two scenes, and if there is no change, then these two would be highly dependent because they should be the same. If there is a change, then what you see, they are different. So the dependence will be lower. So that's the general idea. Changed regions give you weak dependence. Unchanged regions will be high dependence. And once again, I mean, this little c is the key here to say change or no change. And I mean, this, I don't want to go through this. I mean, it's the whole process that you segment and all kinds of things. So this is something you can look it up in the paper if you wish. It just came out in Geoscience and Remote Sensing Transactions. But this is the comparison that, so this would be, I forget which modality it is. So there are two different modalities, and see, the green is false negative. So in these algorithms, we have lots of greens. There are not many greens, and so on. So these naturally are better. So that's what this is showing. So the conclusion then is that copulas, it's a tool. If you have a need to sort of utilize dependence with if you have multiple random variables and they are dependent, so this is something that one could use. I was using traditional ones like the library of copulas for a long time, but more recently ventured into these. Lots of applications, we can fuse multimodal sensors as well as homogeneous algorithms. We can fuse multi-classifier fusion we can do. It is, again, independence is the limiting case of this copula thing. We can do detection, classification, blah, 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 and improvement we have seen. So now I'll leave you with a couple of things that I just learned that people are using copulas in more AI type of things. So this particular paper, what they're trying to do is that they have some software and they're trying to find a single quality score which is interpretable and provides a common basis for decision making. So you have, like, you're trying to, so there is a system and you're trying to characterize it by means of different performance measures. But then if there are several measures, then how do you say just one number? What do I do? So that's what they did, that they came up with a single quality score. So this would be quality metric aggregation, if you will. So then you have a single one. So that's what this paper does. It's a 21 paper. And then the next thing, so anyway, I mean, again, Al knows Kush. I mean, he was the one who told me about it. Did you know that copulas are being, I said, okay. So I just copied this from that paper that just came out. So this is a December 2024 paper. So the idea here, this is an IBM research team, and now people have moved on, faculty positions, this, that, and the other. But the idea is that, so you have a large number of, so metrics that you have, and these metrics, you want to audit different, let's say, models that are being generated, LLMs or whatever they are happening. And what you want to do is, first of all, the synthetic data sets, that you need them to test your models, test your systems. So generation of that, and so you have different performance metrics. You will aggregate them and come up with one score. So that is that, and also you want to focus on preventing bias, discrimination, and all sorts of things that happen with the trained models. So the question is that like audit various generative models and different use cases. If you can provide the framework so that people can test their systems and data and synthetic data, healthcare, education, blah, blah, blah. So this essentially paper talks about the mechanics, the framework, the architecture of such a system. And they, as part of that, this is an integral part. So again, it's a tool that is being used in current AI-based, systems, which is, I guess, important. Everyone is doing LLMs and this and that. Okay, that's the end. Thank you.
Any questions?
Quick questions? If not, then if you detailed questions, we can talk later. Yes.
Pramod, thank you very much for the very nice talk. So my recollection is that in econometrics, they use copulas because they are invariant to monotone transformation of the variables, because they don't know valuations. And that was the primary reason, right? So in your applications, is this a factor? Or, why not use a neural network to model the joint distribution itself instead of the copula?
One can do it that way. Yeah, certainly. That's an option, that instead of doing just the copula, but like the change detection thing, as it turns out, we're just looking at the copula density. And that will give you, if it is 1, that means no change. So again, it depends on your application and so on. And but you are right. We could go, rather than going via class theorem and writing it as the product times the copula, but it was a good way of thinking about it. And that's the one that we use. But now with the neural nets and learning and so on, perhaps there are new ways of doing it. And I guess people are doing it and they want to do it and so on. But that's a good point. We can go directly to it. Yeah.
This is a follow-up on Nikos's question. Indeed, there's a very deep connection between copulas and Kolmogorov-Arnold networks, and in particular rational Kolmogorov-Arnold networks, which would provide the bridge from the copula approach that you're presenting here to a full neural network implementation, if you implement that using these rational CAN network models, deep network models.
So I have learned something new. Yeah. I thought I could retire. No. Thanks. I'll get the reference and we'll talk. Anything else? Anything quick? If not, then I guess it's tea break time, right? Coffee break?
So I have two very naive questions actually. So okay. So one is there any thumb rule to choose this copula function, or it's up to the discretion of the user? Of the system implementer.
Remember, the way we were doing it earlier was there was a library, and we would get, let's call it, training data. And from that, we will infer which model and what are the parameters. Okay. With the neural networks and all this discussion, we can actually learn the nonlinear function, the PDF, and so on and so forth. And so in this case, we don't have the choice. The question doesn't arise, we just learn.
Okay. And actually, I'm not familiar with copula theory. So that C function, the C function, why is it dependent on the? Why is it a function of CDF? If C of f of x, f1 of x.
So let me just, so the joint probability density function can be expressed as the product of the marginals
Right.
times a term that gives you the dependence information. So, but you can convert that to CDF, but it is easier to think in terms of PDFs. That's how I think.
Okay.
So that makes it easy for me, but maybe one can think about CDFs and so on.
Okay, we can discuss offline after this. Yeah. Thank you, Professor Harsney. So we will have a 20-minute break. So we'll reassemble at 11. We'll have a tea break.
इधर करने से तो हो रहा था।
एक बार सर इसको हटा देंगे।
ओके, anyway, तो मैं जाऊँ अब यहाँ से।
यस सर।
the other class, and this whole vector of labels that are attached to these points, these nodes in the graph, that's a graph signal. Okay, so that's a connection. And we're going to use graph signal processing for analysis of the data set, and at the end of the talk, I'll give you a few examples of how we use this information in practical machine learning systems. Okay, so I'll start by introducing some basic graph signal processing GSP concepts. We have graphs that are connections of nodes. The representation of the graph is by a matrix that is a weighted adjacency matrix where if there are n nodes, there will be an n by n matrix of weights. The degree measures the sum of all the edges that go into one particular node, and we will use the graph Laplacian degree minus adjacency. And as I mentioned, the graph signal, typically in this application, the graph signals we consider are labels in a classification task. So it could be also scalar values in a regression task. Graph signal processing basically works on the spectrum of the graph Laplacian or other operators. The eigenvectors, this matrix in this case we consider as undirected graphs. This is a symmetric matrix. We have the eigenvectors, they're all orthogonal, and they represent elementary graphs signal frequencies. They're ordered, they have all positive eigenvalues. And so this eigenpair, frequency and an eigenvector mode, is what we call the graph Fourier transform. So what does the graph Fourier transform mean? You can find the eigenvectors, and you can identify each of the eigenvectors following the solid already quotient problem, where the kth eigenvector is orthogonal to all the previous one and minimizes this quantity, this variation. Now, this variation for the combinatorial graph Laplacian has a very simple, very intuitive interpretation. If a vector is given u, this variation is the difference between the entries at node I and j, right? So this would be, in our case, labels, for example, squared, multiplied by the weight between those two nodes. And so what that means is that this difference counts the most when the weights are the most strongly connected. So if the maximum weight is 1 and the minimum is 0, that means that the variation counts a lot for nodes that are very close in space, and counts nothing if they're not connected that far away. Okay? And so when you find the solution of the eigenvector problem, you find all these orthogonal eigenvectors. They look something like this. The lowest frequency eigenvector is constant, so it would mean in terms of a machine learning problem, all the labels are the same everywhere. And the maximum frequency eigenvector has the most variation, right? And so that means that if you look at neighboring nodes, they have very different labels. All right. So to give you an idea how this can be used in practice, I'm going to consider first a problem of signal sampling and semi-supervised learning. Then we'll talk a little bit more in depth about graph constructions, and I'll give you then at the end some results, some examples of applications in deep neural networks. Okay, so the signal sample, graph signal sampling problem looks like this. This is a representation of a graph. And in sampling, what we do is we identify a subset of nodes that we observe, and the other nodes are not observed. And in sampling problem, what we want to know is how to identify which nodes to sample, how to reconstruct from the samples, and how to know whether we have enough information to reconstruct precisely. To do that, the properties that enable recovery require the definition of frequency that I just presented. Obviously, you cannot reconstruct arbitrary signals. You need to reconstruct signals for which some properties are known. They're low pass, for example. How to sample, there's no obvious regular sampling. There's a lot of work in this area. I'm not going to get into that. And reconstruction is basically graph signal filtering. Okay? All right, so how is this related to machine learning? It's a very popular approach for learning that is semi-supervised learning, where we use both labeled and unlabeled data. And in this setting, if we have a representation of the data set as a graph, as I just described, this representation does not involve labels, right? It's just based on whatever representation we have for the data. The question is, can we decide which nodes to observe, which nodes to label, that maximize the information that's provided by the labeling. Okay, so we formulate this as a graph signal sampling, and then we reconstruct. So we observe these two nodes, for example, and then we reconstruct labels for the others. Now, again, in sampling, things work if you have a signal that has some properties, let's say it's unlimited. So the question is this true for data sets where that we encounter in machine learning? And the quick answer is it's true, at least for simple data sets. In these three examples, what we have here is the cumulative energy as frequencies increase, right? So we have 1,000 nodes, the graph frequencies are 1,000, and you can see in this example that with about 10% of the frequencies, we get 90% of the energy. Okay, so how do we interpret this? Remember that the graph frequencies go from a constant frequency to maximum variation. What this is telling us is that labels tend to be similar in the data set once you consider similarity. So points that are linked in the graph that are close will likely have the same label, right? Now, if you think about it, if that were not true, you would not be able to do classification, right? What you want is some locality in space of the labels of the data sets, then you can separate them to get classified. Right? Notice here that this has a lot more energy compaction at the low frequencies. This is less, this is less. These three tasks are also ordered in terms of difficulty, so this is simpler, this is more complex, also, in the terms of the graph signal variation, remember the weighted sum of the differences in labels across node. This has much lower energy, so the graph signal variation will be less, and this will have higher graph signal variation. Okay, so let's keep in mind this idea for later. Okay, so this is simply to say that graph signal sampling based on the graph structure works better, so let me move past this. I want to spend a few minutes on theoretical justification of why graph signal sampling works. And so assume we have the distribution of the labels, two labels in this case, in space. We have a space of some dimension, and we have the distribution of label 1 and label 2, or red and blue. We draw points from this distribution, and then we construct the distance-based similarity graph, right? So the only information that goes into this graph is the distance and not the label. The label is information that is on top of the graph construction. Okay, and then what we're going to do is analyze the bandwidth for a particular class, right, on this graph, and how it varies with various properties of this distribution. Okay, so we're going to consider two scenarios. This is a sketch of the E, the probability density function for the data. In the first case, we have a separable model, right? So everything on this side is one class, everything on this side is the other class. And then in this case, we have two models that overlap in this region. Okay? So neither of these is a realistic model, right? In this case, it would imply that if you know the boundary, you can do exact classification. In this case, it would imply that we have a region of overlap that is limited. Either it's realistic, but they're good for analysis. We do an asymptotic analysis where the weights are based on distance. We have the graph Laplacian as introduced previously, and we just do divide by n because it's an asymptotic analysis as we draw more and more points from the distribution. And this is a metric of the bandwidth, right? So low bandwidth means similarity between the labels. High bandwidth means very different labels. Okay. So we analyze this as n goes to infinity, and as the bandwidth of the Gaussian kernel shrinks in the neighborhood as we increase the number of points, right? So that basically we have a relatively bounded number of points in the degree that we have. Okay, so this is the key result. There's an information theory paper on this. I'm not giving the details, but the bandwidth in the separable model is converts the probability to the maximum value. Yes? Okay, this is what my students say. You know, I'm a soft-spoken guy. What can I say?
Place the microphone.
Okay.
Time passing. At the beginning, you were doing great.
You know, you should look at my teaching evaluations. All right, so how about now? I'll try not to trail off as we go. Okay, thank you. Okay, so this is the results for the separable model. It says that the bandwidth, right, the higher, the more difference between the labels. It converts the probability to the maximum probability along this boundary, right? And so what this says is that if you, I have an example here. So if you compare these two examples, right? So we have the same density, but in this case, blue happens to be here, red happens to be there, right? And now for the same density, blue is here, red is here, blue is here, right? So if I ask you which of the two is more difficult to classify, you will say immediately this one is more difficult, right? Because you have to separate points in areas of high density. Well, this is what exactly this result says. It says that the bandwidth converges to the maximum of the density of the data along the boundary, right? So the maximum will be much higher here than it is there. And this links the difficulty of the problem, the classification problem, to the locational boundary and the density of the distribution, and to a quantity in the graph, right? The graph band, the graph signal band. Okay, so now I'm going to move on to talk a little bit about the graph construction, right? I just said we just use distance and we connect points based on distance. And so the conventional approach for graph construction would be you have all the points, you compute all the pairwise distances, and then you sparsify the graph by, for example, choosing the k nearest neighbors, right? That's a very conventional approach to do this. But of course, that means that there will be differences in different neighborhoods. You may have these places where the k nearest neighbors are far away, others where they're very close and maybe redundant. And so we wanted to explore an idea to define neighborhoods that capture intrinsic data geometry. Okay? So the idea is the following. So if you look at the weights that we designed before, so these were these Gaussian weights, right? You can interpret these weights as the inner product between two functions in the kernel space. So I and j, each of them representing the two inputs. And then if you think about this, if I give you a point xi and you find the k nearest neighbors, basically you're finding the k functions that have the maximum inner product, right? The maximum correlation. But this is like a thresholding method, right? It just, if you think about the point and all the other points from a dictionary, you find just the k closest. And so what we do here is we, instead of considering just the k closest, we're going to select the best representation in the dictionary. And you do this by solving this problem here, right? And you can think of this as an orthogonal matching pursuit. It will find the best weights among all the neighbors that are considered. So we choose a k large enough. These weights are selected to minimize this quantity. And what that ensures is that the error is orthogonal to the nodes that you have selected, right? So it's a better approximation. This better approximation has a geometric interpretation, which is given here. This is the node that I selected, the node that I'm looking to select the neighbors for. These are the neighbors that were selected by this procedure, and we can show that the nodes that are selected form a polytope around the query node I. Okay, so basically what this will do is, let's say that I start with the k nearest neighbors, then I'm left with this subset of points, and these points form a polytope, and any point that is excluded can be excluded by this condition. You take a hyperplane that goes through this point and is perpendicular to the connection of the query. Everything that is away from this hyperplane is eliminated. So that means that locally, even though you may start with the k-nearest neighbors first, you may have areas where you have 10 connections, others where you have 15, 5, and that characterizes the local data geometry, the local dimension of the manifold. All right, let me skip this. This works better than other approaches, but for the sake of time, I'll skip this. And now we have selected this graph locally. We've extended this idea to creating a clustering or summarization for the data set, right? So if you have the whole data set and maybe too many points, given some input data, we can summarize by selecting a few points. You can think of the summarization as approximating all the data points with essentially a dictionary that is comprised of all the linear combinations of data points and weights. And so we're optimizing A and W. Okay. The two standard techniques the most standard techniques for summarization as such would be k-means, right? So in k-means, you initialize with k the number of clusters you want. You find the nearest cluster center, then update the cluster center, and you do this repeatedly. Right? Now you can think of k-means as a one sparse assignment, right? Every node, every input in the data set is assigned to just one point. The cluster centers are in the data space because they're essentially positive linear combinations of inputs, right? They're centroids. Now, as an alternative, you could consider dictionaries. Now, in a dictionary, instead of doing a one sparse assignment, you do assignment to multiple values, right? So multiple atoms. So it's sparse coding, but sparsity is greater than 1. There are very well-known techniques for designing the dictionaries, and this is a better representation than k-means. The error will be smaller, but it's more costly. However, the atoms represent both data and their residuals, right? And so one thing that we could do in k-means is we could assign to each cluster center, let's say, soft labels in a machine learning application. Now, if you have residuals here, you cannot do that. Right? You cannot really interpret the residuals. The residuals could be orthogonal to the data space. And so what we wanted to do was to create a summarization that would have properties of both, that would include multiple, it would be not one sparse, but k-sparse with multiple assignments, and where the cluster centers belong to the data space. Okay. All right, and so what we do here is we solve the assignment problem using NNK, so that means that the NNK graphs that I described, so given a query, we find among all the 10 candidate atoms the k closest, and this is a non-negative assignment. And then we recompute the linear combination that provides the elements in the atoms in the dictionary. Okay, and this is an example of atoms that we find for the NNS case, and I'll illustrate the difference between the various approaches here. So this is the conventional idea, right, where you do k-means, and basically each of the cluster centers is interpretable. It's a linear combination of the inputs. This is an example of an unconstrained dictionary, and these are regularized dictionaries that are alternatives. This is what we get. Right? So what we have is in this case, this will be a one sparse assignment. Here we can use multiple atoms to represent the data, and but these linear combinations, the atoms, are all still in the data space, as opposed to being in the data space and having errors, right? Residuals. Okay. All right. So move on, and if you have input data like this, you can see how this approach allows you to capture much better the nonlinearity of the data set. So in this example, what we're doing is we have nonlinear data distributions. Each of the colors represents a class. And what we're doing is we're assigning within each of the classes, we create clusters or summarization, and then we classify, right? And these are the boundaries of the classification that you get from all these points. All right, let me skip this, and I'll spend the rest of my talk. I don't know how much time do I have?
15 minutes?
15 minutes. So I'll talk about several applications that we've been working on to deep neural networks, and leave some time for questions. Okay, so the examples that I gave up to this point, they're all, they use very simple data sets and NIST and things like that. So how do we actually work with more complex, more state-of-the-art systems and use these kinds of graph-based ideas? So as an example, this is not not a very complex system. We have the CFAR10 data set. We have multiple layers, and we run this whole data set through all these multiple connected layers, and we can use any output at in any position. And in this example, we have let's say for the 10,000 test images, we will have a graph with 10,000 nodes, where each image is represented by its representation at the output of one layer. Right? Okay, so we can choose a layer. Each image gives us one representation. We create a graph with the 10,000 images. Now, if we have some data set, going back to the example, dogs versus cats, we can construct the similarity between the images in whatever representation. And then we will add the labels to that, and we will have connections between objects of the same class and between objects of different classes. Okay? And so now the graph signal variation here would be we would construct a graph just based on distances. We put the labels in, and then we will compute the graph frequency of that graph signal. And the claim is that if you compare these two cases, right, here you see lots of connections between images that have different labels. Here, the connections that take that are from images with different labels are very long. Therefore, the weights will be small. Therefore, the graph signal variation would be small. Okay. So think of it in graph terms. The stronger the edge weights, the more you count the difference. So here you will have high frequency. The graph signal variation will be large. Here you have most of the strong connections have the same label, low frequency, low graph signal variation. And so what we expected to see was that the graph signal variation before training would be higher than after training. Okay. All right, so the experiment that I'll show next will have for each example in the class C at the output of layer L. So we can do this for any layer, so we may as well do it for all the layers in the neural network. And at the training epoch E, right, we will have an embedding, right? So the embedding depends on the input, the class, the output that we consider, and the training input. Then we're going to construct edge weights, and we're going to see what this looks like. So this is epoch, right? As we train more and more. This is the graph signal variation, right? Basically the sum of smoothness. So lower means smoother. And these are the layers. And starting from layer 1, the most shallow we consider to the deepest layer. Not a very complex network, but just as an illustration. And what you can see is, first of all, in basically all the layers, as you train more, you have more smoothness, right? So basically the training is separating the data so that it's easier to classify. And also the maximum smoothness is achieved in the deepest layer, right? And that's again reasonable because the deepest layer is the one you're going to use for eventually classifying. Right? So the earlier layers are providing some of the feature extraction. The deepest layer keeps the maximum classification, and the maximum smoothness, the best classification, and that increases and improves as you go through. Okay, so this was a validation that we could use smoothness in after the graph construction to evaluate a training a particular machine learning system. So I'm going to give 3 concrete examples of how we use this idea. The first one, recall that the NNK graph construction provides a local polytope and removes points that are redundant. And so what we've done is we've used this local information for classification. So in classification, let's say that you want to figure out if the label of a query point is correct or not, is correctly assigned by the neighbors, then what you would do is you would look at labels of all the neighbors and do a weighted average of those labels. If it's a binary case, you would see what is the most likely among the neighbors. Okay. And so what we did as an experiment is we designed a system with a usual fully connected final layer in the neural network, but then we ignore the fully connected layer and do this geometric local classification to see what happens. This geometric classification tells us how the embedding allows us to do classification. A fully connected layer may allow us to do things like that, where we have a very complex, large number of parameters. We're able to create a boundary that overfits the separation. Sorry, this is very small. Don't expect you to read this, but just to mention this application, we were considering the out-of-distribution detection. These examples are for data sets in natural language processing, where again, it doesn't matter whether it's images, speech, or natural processing, there's an embedding. And one of the most successful methods for out-of-distribution detection, essentially detecting whether data is consistent with what you observe and you use for training, is to simply compute the distance between new data embedded and old data. And a very typical method is to use k-nearest neighbors and store essentially the whole data set. Right? So you store the data set, you want to see if something new, you can give a reliable answer, you compute the distance to all the input, all the data in the data set, and if the distances are large, then you would say this is out of distribution. So to make this faster, what we do is we use NK means, so basically our approach for summarization. And the main result is that we can do as well as k-nearest neighbor, but with a fraction of the storage. Much faster inference. All right, so I'm going to conclude. I think the main takeaway, I went quickly, but the main takeaway is that we construct graphs from data, right, using a representation of the data that can be an intermediate or late layer in a neural network. The concept of graph signal variation is simply a measure of differences in, let's say, labels or other quantities across the graph, right, that it takes into account both the label and the distance between the points in the graph. And I talked about what to label, how much to label, how to form a similarity graph, and some results in more practical settings. And I'll conclude with a bunch of pointers to code. And if you want to learn more about graph signal processing, there's several overview papers, including on applications, for example, sampling, and a couple of textbooks actually. With that, I'll conclude here. Thank you. Questions? Yeah.
Thank you very much. Very interesting overview. Actually, thank you. So, those there are those constraints about the no? Yeah. I think I can speak loud. Yeah.
Yeah, thank you. Yeah, thanks. Nice overview. And one thing, when I started kind of looking to those graph signal processing, I just noticed, so basically, it's about statics. signals, right? Mostly. So you don't consider dynamic. It's not like PDEs, it's not like cellular neural networks of Chua. So my question is, I mean, there was this nice theory in the 80s developed, and basically they attack about the same problems. When you are actually telling about neural networks, are you aiming at convolutional or cellular, basically, in application? Because I see that might be a nice, maybe line from, let's say, graph signal processing towards kind of dynamics of cellular neural networks, and perhaps some kind of like joint application, I don't know.
Quick answer is I don't know. I haven't thought about that. I think as I mentioned, one advantage of this approach is that you abstract the architecture. I guess you're saying if in a system that is dynamic, maybe the embedding changes over time, and then therefore the graph connections change over time as well. In fact, that's an interesting question.
I just want to say, yeah, there have been works on dynamics, right? You can consider multiple graphs as instantiations of samples at different points. And then you have, as Antonio said, you may have different adjacency matrices per graph, and also the connectivity from one time slot to the next is also, so this is where the tensors that also Professor Sideropoulos mentioned about. But there have been, and actually you can come up with developments like the Kalman filtering for inference across time.
Yeah, this also makes me think about graphons and methods.
Yes, the Alejandro's group, yeah.
Any other questions?
Thank you.
So thank you, Professor Ortega, for the exciting talk. So our next speaker is Professor Georgios Giannakis from University of Minnesota. He is going to talk about kernel-driven self-supervision for learning over large-scale graphs. Welcome, Professor Giannakis.
Thank you guys hear my volume is enough? I can speak loud. So, am I okay or? We're okay? Okay. So, first of all, let me thank the organizers for their efforts, for inviting me here. And Vijay in particular, and Anantram from ARL. I have been at least half a dozen times that I wanted to come to India. Something was happening, I could not. But my exposure to India was Anantram Swami. He was my office mate when Antonio was not in the 80s, right? When Antonio was faculty there. You see? Then I had myself a number of outstanding PhD students and postdocs from India. One of them actually is now with IIT Kanpur, Rajavat, Vietnam. And another one now at Wisconsin. And we will hear from ICASSP, Sanilita Samshunder. She's a plenary. So they exposed me to the culture that I really feel near and dear. Okay. So today here I am, Delhi, and I will talk about self-supervision, something that Antonio also touched upon, and kernels. It was a fantastic introduction for my talk. And here I want to acknowledge the NSF, not the one that is on the water bottle, the US NSF support, and the people who contributed to this, like Alireza Sandehi and Konstantinos Pouliou. Okay. Motivation. Clearly, graphs are everywhere, and as Antonio also talked about, we may have real networks that are agents interconnected, such as the smart power grid with cables. That's what I mean by real networks. But you can have networks or graphs that are also built on similarities, like these red guys are close to the blue guys. And actually, Antonio said it very nicely, but I like to use a Greek way, a Greek saying, proverb, which says, tell me your friends to tell you who you are. That's basically the networks built on similarities are all about. You draw a connection if you are friends. And just to focus on a problem, the objective in many cases is to infer values or labels of nodes from a subset of nodes. For example, in citation networks, right, where you have two papers, if they're cross-referenced, they're connected with a line. And then the label could be ICASSP, another conference you want to select, right? However, a challenge is associated with what people like to call semi-supervised learning, especially whenever you have large scale graphs, and it may be challenging to label them. So you have a subset with labels. Why it's challenging? Because things of privacy show up. Recent things in the United States reminds us of this. The labeling is costly, can be costly, and there are perhaps unreliable human annotators in a crowdsourcing setup, right? So, with this motivation, the outline of my talk is the following. I'm going to identify challenges when the labeled nodal data on a graph are limited, okay? Then I'm going to start talking about self-supervision, my way of understanding self-supervision, with an abbreviation that is more, reminds you of Asia Pacific, SESU. Self-supervision. So from unlabeled data, that can be abundant. So we may have a lot of unlabeled, but limited label. And then I will demonstrate how SESU can be realized through embeddings, which are basically lower dimensional vectors sitting on every node. And I will not only draw from kernel theory, reproducing kernel Hilbert space theory to identify the kernels to help me, but also I will try to learn kernels. So therefore, come up with learnable SESU models to have some sort of optimality. Then I'll touch upon some performance through regret analysis, and depending on time, I'm going to talk about multi-view, multiple views, and multiple graphs that were brought up for the dynamics. Okay, that's all. So let me talk first about semi-supervised learning. You have a graph with vertices, adjacent symmetrics, weighted or unweighted captures connectivity. So you have n nodes, and therefore n by n adjacent symmetrices, and you may have extra feature vectors sitting per node, okay? Educational level, whatever, the selection of recommended systems and so on, salaries, data, and so on. So, but what we typically have are noisy function values, and the goal is if I give you the graph, this is for for learning purposes, if I give you the graph A and X, and I observe a subset that I have a subset of nodes in calligraphic O for observed, with cardinality n sub O, which is much smaller than n. This is what I said, that the labeled, the observed data are limited. This is where it comes. Relative to the number of nodes that I have. And if I give you this, I want you to infer the function values at all nodes. Okay? So I'm trying to find a learning function, and here is what I'm going to suggest. That at node n, look at the nth column or row, or column and row, concatenated, A sub n. These are the neighbors that we're talking about. This is what is described here. And the xn. So I want you from now on to think of an as an extra feature vector, in a way. Right? So you can, in principle, look at it as an xn. But this is nice, because even if I don't have xn, I can do something with an. I can do machine learning with an. So if you know how to play with classical machine learning, you can, from now on, translate that to graph-based machine learning. Okay. Okay, what are the challenges? Challenge number one, because you have the number of observed to be small, you lead to underdeterminacy. So the question is, what are suitable regularizations? What are suitable priors that can help you? How complexity is affected? And what I call SESU, self-supervision, how can this help? Can also unlabeled data, AN, be sufficient for inference? That's another thing that I will argue. And this is important because in many cases, as in graph neural networks, there are the values x. If you don't have feature vectors x, you cannot run a graph neural network. But I argue you can replace the ax with an and do so. Okay, so this is semi-supervised learning over graphs. Now, why? All right. Now here is what I used in my title, kernel-driven. What about kernels? Suppose you have labeled data, observed, and we want to learn this f of x of n plus en. So what this RKHS approach says, if your function that you are looking for is a superposition, or a weighted superposition of bases, kappa xxn, if that's the case, okay, then if you confine the set of functions to lie on this space, which is not too unfamiliar for someone in signal processing, right? If someone tells you, take a basis and put it on every sample, xn, then you know that this is what we do when we do sampling and reconstruction. All I told you is that a kernel that we learned, but we learned it as, is the sinc function, okay? And of course, this is a sinc function because you assume band limitedness. You may have other constraints. Okay. So, in this case, if you're trying to find the minimum over the set of functions, of the function that minimizes this fitting loss and a possible regularizer, then Waba in the 70s came up with this beautiful result. It says that although this is a function optimization, you can turn it into a coefficient optimization and look at the estimate as an inner product of a kernel constructed vector kappa x and a set of coefficients c. So the optimization is clearly familiar to us in signal processing because we understand what the ridge regression is all about, right? This is a ridge optimal. So you have the loss in the n observed, and then you regularize it with kernel metrics, and that yields what we, in other contexts or similar contexts, we call LMMSC, right? or Wiener filtering, and this is the C hat. Okay. What are the problems here? Computational complexity is cubic, and it can be prohibitive if you decide to do NO, okay? Because this is of size NO by NO. Inverting it is incurs cubic complexity. Also, this is the key observation we have. The solution here from WABA does not leverage unlabeled data. So you may have abundance of unlabeled data and you don't use them. So, even if though you can show that through self-supervision this is possible, the best kernel over here is presumed to be known, but the best in what sense is generally unknown. But once identified, what you learn from this slide is that you can estimate the learning function f hat. Okay, that's it. Now, what is SESU? Because I asked myself, can SESU help here? What is self-supervision? Self-supervision with the block diagram has two branches. The top branch starts from the even unlabeled data, and using a reference box, you can obtain Y new reference, which is if you pre-select this function. I'll show you some trivial examples to relate. But generically, you start from a function. This function is the rotation that Antonio presented, right? And then you know this rotated image. But then I will ask why rotation, for example, is important. I will ask questions like this. And then in the lower branch, you start with a neural network that has, let's say, theta sub E for encoder parameters, and this yields the reduced dimensionality rho x nu, which is basically what I called embedding, the lower dimensionality. And then you have a decoder, theta d. So you train this lower branch to yield, to have an output that is as close as something that you are confident about. Okay? And you minimize the loss. So are we clear? What do we mean by SESU with low dimensional embeddings? Remember, this dimensionality here of little d, the dimensionality of rho of little d, can be much smaller than a no. It can be as much as you can afford. Not as much as you can afford computation. Okay, so is that clear? Now, what is nice about these embeddings? The nice thing about these embeddings is, and this is what I argue is our contribution, is that they provide with an inner product estimate of the kernel, an estimate of a kernel, through which you can learn F using ridgeless regression. So if you can substitute from kappa in the Hilbert space expansion of the function a kappa hat, then all of a sudden you can combine the rho transpose x with xn and come up with a regression that depends on the input that you have. But what is critical is that you get a parametric model of dimension little d. Typically, kernel approaches are non-parametric approaches. And here, what I have done is to convert them into a parametric approach, theta. And the attractive features are that the output of the embeddings, the rows, they leverage the unlabeled input data to estimate a kernel. And the logic and intuition behind it is the following. If the kernel estimate is good, my function estimate will be good. Okay? So it is an intuitively appealing way of looking at the function estimate down the string. So, and also with d less than an O, the complexity reduces to OD cubed. Okay? So basically, these are the attractive features of the embeddings, raw. Okay, now, let me give you SESU models that have been available or can be thought of. One of them was the rotation that already Antonio covered. But let's look at principal component analysis. The top one could be just the identity. You start from xn, okay, the reference is xn. Then I'm trying, through now, not a neural network, but a linear operator, the u, which is the eigenvector of the sample covariance, right? I'm trying to, this is if I collect all the parameters into theta e and theta d, for the, we know the encoder and we know the reconstructor, decoder. And then we know that the output would be x hat nu, the low rank approximation of x nu, right? So this is basically the d by 1 embedding. So this is what I'm solving out here. And I will find the well-known sample covariance and the corresponding little d eigenvectors. So, but since we understood that, you can go nonlinear also, right? This does not have to be a linear operator, a matrix. You can use kernel BCA, or you can do nonlinear autoencoded, auto-encoding, but the kernel approach is not appropriate for decoding. So that's why in the special case 2, I have picked up a nonlinear one, the nonlinear autoencoder, where I train with backpropagation end-to-end the theta parameters of the encoder and the theta d of the decoder, right? And of course there are also Bayesian alternatives which lead to dynamic, to generative AI models, okay? But now we know what is SESU, right? These are examples of SESU. Now, let me tell you what is the kernel-driven SESU. It's a principled way of approaching the kernel-based learning. So, this is the well-known Mercer theorem, right? That every nonlinear kernel is nonlinear function phi to be taken of infinite dimension, and then it boils down to a linear inner product. So what I'm saying here is that the kappa hat should be replaced by the embedding. And then in the output, you should not look necessarily about rotations. It may be good to look, but it is safe to look at matching the kernels. So basically my approach here suggests if you want to find self-supervision, then match the kernels. And why? Because exactly because the downstream estimation will be accounted for through the parameter theta. And how do you find the theta? Whenever you do semi-supervised learning, you are given the xn. Notice that you have labeled and unlabeled. You are given kappa, and you are learning the embedding as I explained earlier. Now, after you know the embeddings, you use the embeddings over the observed input-output samples, and you find the theta in the standard way with or without regularization. Okay? So, what is the key idea? Self-supervision creates low rank or low dimensional approximants. That's one thing. Okay? And then the low dimensional approximants help the downstream learning guy. So basically, I'm suggesting self-supervision should include that. Okay. Now, I clarified from my title the kernel-driven blah blah. I also have the adjective learnable. So I argue that you can learn. You should not be happy with a prescribed kernel, but you can learn what is the best performing kernel. Because you can ask yourself, how do I know if the kernel you picked is the right kernel? Right? Okay, the learnable SESU starts from a dictionary of kernels. So corresponding RKHS's spaces, they're reduced by these kernels kappa p, and then for graph, given the data xn, you learn the embeddings to approximate the phi p in a way that you have a linear convex combination of kernels kappa p. And this convex combination yields the same convex combination of the estimates corresponding to each and every phi f hat sub p. So what is the idea here? If you have a multi-kernel dictionary model, this builds a richer class of functions you can approximate. So, and the task is performed, as you can imagine, by looking at all p from 1 up to p. You optimize over the weights, and you optimize over the function estimates, perhaps with prior knowledge placed on regularizing. So this is the learnable SESU that I talked about, I promised. So starting with a dictionary, you can be whatever you want. Complexity is only the issue, but you can have Gaussians with different covariances. You can have linear, you can have RBF, and so on. So you initialize with WPO, and then you acquire data per node, and for every node, you extract the SESU embeddings, the rows sub p, different for every kernel p, and then given the xn's over the observed and the row for all the p's, you update the main task function parameters by using the previous iterate point online, previous sample, with the gradient correction. This is a gradient descent approach, which can include the loss function and the regularizer, prior knowledge. And of course, you update the weights in a multiplicative fashion, which is actually arguably stronger. But you can intuitively look that if the cost is very high, then this WP will, in the next point, will become 0, right? So you can then normalize them to look like a BMF, and then you can update the function for each and every p, and after you do so for each and every p, you sum it up and get the final learning function. So the inference basically depends on the embeddings and the thetas that you found. Okay? Now, if you have multiple views, then what you can do, you can basically, you can have images, and text, and speech, and what have you, but you can find a common embedding, rho n, and then train, always in the output we have the kappa, right? From each kappa 1, kappa, capital V, V is the number of views. And then you can train each and every view to find different parameters of the encoder and the decoder of the self-supervision. And the function estimate will come up by the usual form that I used so far. There are some experiments with small scale data sets, the stochastic model, the temperature, and the network delay. And then as a reference, this is what I'm using. But here, the dimensionality, little dimension is 15 on the embedding, 10 and 4 for the network. And the figure of merit is the normalized mean square error for the unobserved and sub u. So here is to see that here is the normalized MSC, the lower the better. And this is for the kernel PCA, and this is for the autoencoder. And we are down here with KLSSU. And similar for all data sets. The bottom line here is that the KLSSU, KLE is kernel learnable, right? Semi-supervised outperforms benchmarks in order of magnitude in network delay data sets. Okay? This is when we learn things. Again, we combine multiple kernels. We observe that it improves performance indeed. And I here want to show you what happens if, for example, you have over here on the left, you have using only the AN. And this is over here using the additional embeddings, XN and AN. And you see the ones that are lowest are the ones that utilize multiple kernels. So searching for the kernel pays off, sometimes an order of magnitude in normalized mean square error. And then we compare favorably, as I said, with graph neural networks because they cannot do without. So this is how much favorably in normalized mean square error. The graph neural networks cannot perform without X's. Okay, multiple views, I don't want to. Contributions so far in context. I basically, there are different approaches that people have tried for self-supervision. A popular one actually, in addition to the rotation, is the so-called masked data modeling. So basically, you have an image, right? And then you sample different parts of the image, and some of them you pretend that you don't know, you mask. And with the rest, you're trying to predict the ones that you skip. This is very popular, and it has shown in medical imaging impressive improvements. And the key contributions here are, we somehow have a principled way of saying this self-supervision can leverage updated data and can adjust to the learning task. That's our claim. And the priors can use either a single kernel or multiple kernels, and it can be proceed online. So the one that I want to spend a couple of minutes on is some theoretical analysis, performance analysis, which basically relies on the cumulative loss, that is this term, of the f hat, minus the baseline, which is the best fixed strategy, f, this is a common f for all, in hindsight. And for that, we have utilized the so-called neural tangent kernel, which is the expected value, sort of a gradient, transpose gradient of the function f. And the reason we adopted this is because we can make solid claims and basically argue that if you give me a deep neural network with finite width per layer, then this NTK, neural tangent kernel, guarantees this following result in our setting. That the kernel XX prime and the kernel approximation kappa XX prime and the kernel kappa hat XX prime, which is provided by our embeddings, is bounded. The probability of being large, greater than epsilon, is bounded by this exponential function. So, and you can imagine, if you have a worst case kernel estimation error, kappa hat minus kappa, this bounds the function estimation error, f hat minus f. And that leads us to the following result, which says that if you select the loss function to be convex and bounded, and also its derivative to be bounded, then under these assumptions that is up to you to select, the algorithm attains this regret. This is the regret, I remind you, is this difference. So it is what people like to call, it exhibits sublinear regret. So if you divide with 1 over n, that will go to 0. Okay? And just to show you a couple of real data sets which are a little bit larger scale. This is about 20,000 nodes. This is called a energy data set. They basically put in a house in Belgium. They measure temperature in different rooms every 10 minutes for I don't know how long. Anyways, then what you see here is that the cumulative MSC goes down. That means that you have basically sublinear regret. This corroborates our analytical result. And this is the air quality data set. Now, instead of Belgium, this is collected in Milan over a year. Hourly responses from chemical sensors, and they were trying to find YN, the concentration of dangerous ones. Okay, so this one basically says that indeed this approach has a hope if you allow n to be large enough to get to the true learning function f. Okay, this is what I mentioned earlier about the dynamic. This is how the multiple graphs look like. And you can imagine that you have kernels that assess similarity per slice and across slices, like the inter, and intra kernels. The moment I can have kernels, as you can imagine, my theory can go through, right, with self-supervision. And the kernels can be of different type. Can be continuous features. It can be also over continuous analog amplitude features, and also the adjacencies across nodes. And you can have kernels for categorical features, which are basically one if the two n and n nodes have the same, belong to the same class. And there are space and time kernels. You can think of in time the dependencies dying out if one minus rho to the difference tau minus tau prime. Nevertheless, what I'm saying is the theory I outlined through for self-supervision over a single graph, it can apply to multiple graphs. That's basically what it is. And it can apply also to dynamic resource allocation. I don't want to talk about it. It's okay. So what are the takeaway points? The self-supervision is a valuable tool when you are dealing with a limited number of labeled data and an abundance of unlabeled data. That's number one. A principled approach to defining self-supervision would be using embeddings that are adapted to fit the main task. That's what I did, the kernel. Because the kernel is basically defining the task, the coefficients that you will find in the parametric model specify whatever you want to estimate. So it can be manageable, can have manageable complexity and online operation. The analysis establishes sublinear regret relative to fixed section approximation. And for dynamically evolving graphs, you can have space-time signals. And the road ahead is basically probabilistic SESU, or self-supervision. And as I said, if you adopt a variational autoencoder, you can have the embeddings drawn from a Gaussian distribution or a convenient distribution, and that can give you a different output, which will enable AI, for example, using diffusion models or generative AI. So this can be used, in other words, not only for self-supervision, but also for generative AI. So that's all I had to say. Thank you.
We have time for questions.
Nice overview, Georgios. Yeah, nice overview. I like that. I was also thinking that in many of these multi-view problems, especially when you're looking at asynchronous multi-view, so health, for example, you have different measurements at different periodicities for clinical visits versus if you're wearing a smartwatch, you have a different sampling rate. So one of the advantages of kernel methods is that they can very easily interpolate between multi-view missing samples. So is that one of the motivations, or is that a side benefit? And to what extent can you accommodate missing values with these kernels? And is that, and do you
You said it already.
Yeah.
That kernels basically is like doing interpolation with sinks.
Exactly.
Okay?
Yeah. Right.
Non-parametric methods have this feature that you said. Very
Yes.
Nicely.
Yeah.
Okay.
But the issue is that does it change your choice of kernels if you have some, say you know what the periodicities are, right? For
Yes.
your smartwatch measurement of heart rate versus you visit the clinic, once every week, right?
Understood.
Then does that help you determine which types of kernels you would use, or is it agnostic to the missing data?
No, it's clear that if I have information about, the more you give me, the more I take, right? For example, if you remember, if you noticed, if you tell me, I have this is relevant to the comment I made, that I'll give you another example since we are here. But see, if you, this is the spatiotemporal, right?
Yeah.
If this is an exponential decay. That means dependencies are not there as, or as you go further away from one another, right? If someone tells you this, well, this is the memory of a stochastic process,
Right.
in some sense. So then you might as well build it in your kernel. So, and to be fair, right, I say learnable kernel in the following sense, that still, instead of committing to one kernel, I'm just saying, give me as many as you feel are good for this function. And then I will tell you which ones to select, if it's only one, or the first two best, or three, or whatever. I know how to play that problem. I know how to deal with that problem.
Yeah.
So,
But I think you have another constraint. With the missing data, I think you have an additional constraint you would need to consider, because the choice is, let's say you've chosen the first kernel already. Now the second kernel, if you have missing data, let's say temporal data, you might want to shape that kernel differently so that you can account for better interpolation of the missing data, right?
yes.
Yeah.
So you want to say?
Yeah, actually, just to add
Yeah.
about the same.
You're correct.
Yeah.
No question.
Yeah, it's actually what I was thinking is exactly like we're talking about reproducing kernels, Hilbert space, and let's say splice would be a typical example, interpolating splice.
Yeah,
and you are
also,
basically
when
doing
the
that.
second derivative is bounded, that's
Exactly,
minus.
and you are doing that. And in fact, this is connected also with rotation example, because rotation is interpolation itself.
Yes.
So it's like, again, you can do the same. My question was more about the, say, limitation. Let's say when you are considering separability of the kernel, you have this approximation.
Yes.
How accurate this approximation is? I mean, let's say
No, there are-
ideal case versus what you can actually do.
Yeah. there are basically, don't forget that I can adjust the weights also, right? Adjusting the weights can be, I can select only one kernel if you tell me I know that this is the best. So,
But measuring bias, how much you can go.
yeah, basically there is a bias variance trade-off for sure.
Yeah.
That's actually, this depends, this also influences the size of rho, the embedding. If you allow me to, if you don't care about complexity, you allow me to keep the rho, then I have a very good estimate in that sense. But
Did I understand correctly that it's going towards no parametric regression models? The way how you are actually.
actually, this is exactly the point I'm trying to make. Instead of, this is also, what I will say is also true with what people like to call random features. Although kernels are tools for non-parametric estimation, and we know Gaussian, kernel smoothing estimators for PDF, for probability density functions, right? That are well known. 70s, 80s, 90s were full of papers in the statistics literature. But in this particular case, the fact that I select the theta, the rho, to be my regressor, it has dimension d. And I can play with this d. And I'm saying playing with this d will influence the bias variance trade-off. That's my hunch. And definitely complexity. That's why the guiding principle would be how much complexity can I afford? Yeah.
So, the degree bound, you had a term called width. So, what is that?
The width is how many layers you have per layer. So how many neurons you have per layer. The depth is how many layers, and then the width is how many neurons. Yeah. Lunchtime. I will be around, so we can chat.
So we can thank Professor Giniakis for a wonderful talk. So I would like to invite Professor Prasad, ex-director IIT Delhi, to say a few words about the workshop. So you can go to the podium.
You know, one thing that you don't know is that if you indeed, now I remember things, you indeed attended the Lake Tahoe meeting. That was, I was co-chairing it with Anantham Swami. And most likely, we have gone through your paper. So, who? Oh boy. Thank you so much.
But you also wrote a very long review.
That is bias variance trade-offs. Okay. You can, I think you, whoop. Oops, here we are. Oh, this one is good. Let me try. Okay.
Thank you very much. Thank you, Monica, for calling me here. Although I don't understand why you have called me here, because I have definitely gone past my best before date. So, no, I don't think so. So, anyway, it is a pleasure to meet such stalwarts of the area of signal processing. And what is even more encouraging for me at this late stage in life is that probably signal processing is not giving way to AI. I think signal processing is going to remain the foundation on which AI will be built and machine learning will be built. I think from the few talks that I heard just now, there is no doubt about that in my mind. Because without that foundation, that fields like signal processing can give to AI. So I think this theme of the workshop is more stepped, very well chosen, and the speakers are doing a great job at this. I think that's all I can say. I really don't, I'm not doing much in this time. In fact, I did make an attempt to get into AI, perhaps as late as about a couple of years ago. We wrote some paper from a signal processing perspective, and we are having great difficulty even finding a journal or a conference who would be interested in even looking at the paper, because they don't find it very relevant for some reason, because they say that even without a review, the paper is sent back. Please try another journal or another paper. So I think I'm very encouraged to see that unlike my efforts, other efforts are going to be much more meaningful. Thank you very much for this opportunity to come by, and thank you for this. Thank you very much.
So lunch at the first floor.
Yeah, lunch at the first floor, sir. Yeah.
Yes. So we'll gather back at 2:30. Yes, for speakers we have a special lunch arrangement at guest house.